Hello everyone. Welcome to today's webinar. Thank you for joining us. My name is Shiny from Mydbops, and I'll be your host for today's webinar. And we have a very interesting topic, the evolution of replication in Postgres. So Postgres, it has changed a lot over the years, and we are going to look out how this replication started with simple triggers and how it has evolved over these years to the powerful systems as we use today. And but first, let me take just 1 minute to introduce who we are at MyWebinar. We are a trusted database management service provider. We provide managed and consulting services. So as you can see on the screen, we are nearing a decade of expertise in this field, and we are very proud of the scale at which we operate. And we don't just do Postgres, we support a wide range of technologies, including MySQL, MongoDB, MariaDB, TiDB, Cassandra, AWS, and everything. So now let's get to the main event. I would like to introduce our speaker for today, Anuja P. from Mydbops. Anuja is going to take us on a journey through time. So she will be covering the early days of trigger-based replication tools that we used in Postgres and how physical and logical replication works, and the brand new replication features in Postgres 16, 17, etc. So before we begin, a quick note. This webinar is being recorded, and you can post your questions then and there in the chat and Q&A section. We will take questions at the end of the webinar. So let's get started. Anuja, over to you.
Yeah. So let me share my screen.
Okay.
Okay, let us get started. So welcome all to today's webinar. So we'll be discussing about the evolution of replication in PostgreSQL, and I'm Anuja. Yeah. So these are the introduction slides about MyWebinar. Shiny has already given a view on our MyWebinar, so I'm skipping this. So the agenda for today is how replication has evolved from a trigger-based system to core feature. And since replication uses a WAL file, we'll be having a discussion on WAL and its architecture. And then comes introduction to the physical streaming and logical replication, and what were the further enhancements in replication, and few questions and answers will be discussed and the key takeaway. So before getting into the evolution of replication, we should know what is replication and what is the advantage of having it. So replication is having copies of the data in multiple servers. So when you have such kind of multiple copies, you'll have two advantages. One is high availability. Say the primary node fails and you want the data immediately. What will we do? Yes, we have the standby for that. So whatever data we have will be copied in a standby, and from the standby we will have the data. And another one advantage is scalability. So just consider I'm going to load my primary with both read and write operations. That is going to cause performance issues. So in order to overcome that, I can have my standby only for my read purposes. So that will decrease the load and balance, and my performance will also increase. So let's get into the evolution of replication now. In the year 2010, in the version 9, physical streaming came into introduction. So this was a foundation for real-time replication. So physical streaming is like the entire database clusters will be streamed to the standby. So this physical streaming had some issues, some problems, which was addressed in the next version, which was introduced in 2014, version 9.4. Regarding the problem, we'll be discussing in the upcoming slides. So I'm just giving a gist on the problem. So the replication slots was introduced to overcome this problem. And in the version 9.4, we also had the logical decoding feature. So logical decoding was the base for CDZ. which is used for getting the data analytics to different non-Postgres systems. And in the version 2.7, in the year 2017, version 10, we had the PubSub framework. So this is where the major change took place, where the native logical replication model came into existence. So it also supported cross versions, and so far we had like the entire database clusters are being replicated to the standby. But now we have the feasibility of replicating only the particular table that you want to get it streamed. So in the year 2022, in version 15, we had an additional feature of filtering row and columns. So we were able to replicate only selected columns and selected rows. So this was a major milestone. And in the year 2023, the version 16 introduced parallel apply workers threads. So this was used for enhancing the performance. So it was like though we had multiple core CPU, the replication was done only through a single thread. So in that case, I want my replication to be done through multiple threads. What can I do? Yes, I can enable my parallel worker threads, and I can increase my performance, and my lag will also get reduced. And in 2024, in the version 17, the failover slots or the failover control came into as a feature where the high availability of the node came into existence. The early era, so this is the version prior to version 9. So this was the age of trigger-based tools. So in the early ages of Postgres, replication was not considered as a part of database engine. It was considered something outside it. So the community built external tools such as Lonnie and Londist, and which were purely trigger-based tools. So when a insert, delete, or update occurs, a trigger will be fired and it will cause the events to be written into a log table. And from the log table, the changes will be given to the actual table. So this system came with few limitations. We had write amplifications because we need to write once into the actual table and once into the log table. And the DDL schema changes were hard to manage because we need to create the schema changes in the standby and then we have to replicate the data. So this was not an automatic method. And the system was very fragile to say, because if a trigger fails, the replication will break. So here is an illustration of the workflow of Sloanie 1. When a user triggers any query, like may say insert or update or delete, this will fire a trigger and it will log the events in a log table. So from the log table, it will be replicated to the standby. So before getting into the introduction of replication like physical or logical, we should know what is a wall and what is the purpose of it and how it looks like and all those things. So wall is write ahead logs. So this wall enables the physical replication in Postgres. Wall is like we will have all the data changes recorded into the wall. So before any records modified are being written into the actual file, the records will be first applied into the wall file. And the wall provides data integrity that is, it was used for crash recovery process. So next, let's get into the wall architecture. So when a client makes a request in the form of transaction, say or insert, so the transaction manager will initially handle it, like it will assign the transaction IDs, the state of the transaction, and whether a lock is required for that particular transaction. Everything will be managed by the transaction manager. So this will be given to the wall manager, where the wall records log entries will be created. And these entries will be written in a wall buffer, and from the wall buffer, the data will be given to the disk wall files. So what is the need of a wall buffer here? So that is a very important point. So the wall buffer is an in-memory component. So it is in your RAM. Just imagine if you're going to write each and every log, each and every time into your disk. So this is going to cause high input output operations, and this will impact your performance. So when you're going to do it through a wall buffer, a set of logs will be written together into the disk at a time. So this might increase your performance. So that is the use of a wall buffer. So when we consider the in-memory components, as we already discussed, the wall buffer is an in-memory component. In addition, you will have the buffer pool component. So the buffer pool, once the data are written into the wall file, the modifications will be written into the buffer pool first. So it is a cache memory. So instead of fetching the recently modified data from the data files or from your disk, you can pull the data from your cache memory. So this will increase your performance. It will make the system efficient. So the disk storage components are your wall files and your data files. So the wall files is also stored in your disk, and the actual data files is also stored in your disk space. So next we are to discuss about the wall sender and the wall receiver. When it comes to the point of replication, the wall sender and the wall receiver plays a vital role. So the primary server has the wall sender. The wall sender will read the wall file and it will stream the records to the standby. In the standby side, we have the wall receiver, which will receive the records and it will write it into the wall file and then apply the changes to the data files. So if just consider a node A connects with multiple standbys, then you will have wall sender process, multiple wall sender process accordingly. So because of this wall sender, we have continuous streaming. The data is being you have the data integrity, and the performance is also good. Yes. So what a wall contains? So the wall contains physical data. So you don't have the logical support for logical data. So it is fully of physical data. So it will have the data level physical changes. It will have the page level modifications such as your block number, your offsets, and you'll have the transaction details such as whether the transaction is committed or aborted, and the redo informations. So where the WAL files are stored, in which directory? Till the version 9, your WAL files were stored in pgxlog, and from version 10 onwards, it's stored in pgwall. And when you consider to the segment size, that is, what is your WAL file size? The default is 16 MB, whereas you can tune up to 1024 MB. So this is a detailed like a structure of your WAL file. So as I already told, your WAL file is not readable, human readable. It will be in binary format. In case if you want to read it, you can use your pgwall dump to read it. So it contains a resource manager, length, transaction description, and few other details also. So resource manager will tell you what kind of transaction it is, whether it's a heap in the sense that the actual data change, and what kind of transaction, whether the transaction is about or a commit. And the length will include like the record length, and the total length is your length of the data plus the payloads. And TX is your transaction ID, and description gives you about the operation details. So yes, so your binary files in WAL will contain the actual data as well as the metadata. So we will see how this WAL has evolved from basic logic logging to intelligent failover. So the WAL was first introduced in the version 7.1, which was purely used for crash recovery. And from the version 8.0, it was used for point-in-time recoveries. From version 9 onwards, it was used in physical streaming replication. And in version 9.4, it was used along with logical decoding. And from version 17, it's used in failover controls also. So let's get into the physical replication. So this was the start, or we can say it was the start point of replication in the Postgres history. So from version 9, we had the physical streaming. Physical streaming is, or physical replication is, the entire database clusters by block will be replicated to the standby. So it purely relies on the wall logs. So we can say that primary will generate the wall file and the wall files will be streamed to the standby. So this version 9 gave us a feature of hot standby, which means you will be able to read or execute the select queries during the recovery. And when we consider the advantages compared to the previous trigger-based system, the architecture became strong because replication didn't break because of any log when we just stream the data. And automatic DDL, we need not create any DDL, the schemas in the replica. Automatically, the DDLs will be replicated. And we didn't have any write amplification, so the overhead was low. The replication slots. So when we consider the replication slot, the problems which were in the physical replication was overcome through the replication slots. So the replication slot was introduced in version 9.4. Before that, we should see what is the problem, right? So the problem is, from the primary, the wall files will be given to the standby. But the primary didn't have a proper mechanism to track what is the current wall file which is being used by standby. So it will not retain the wall files, and there were chances to delete the wall files which were still needed by the standby. So this was a major drawback because we had our data being lost and also the replication failed. In order to overcome this, the replication slot was introduced. So from the primary server, when we replicate the wall will be replicated through the replication slots to the standby. And this replication slot acts as a bookmark. So it will tell the primary what is the current wall file which is being used by the standby, what is the current LSN number, and please don't delete that particular wall file. So because of this replication slot, we had wall retention, the data with safety, and also we were able to track the status of the wall. I mean, the standby, what is the current LSN number, and all those details. So along with the feature of replication slot, version 9.4 also introduced the logical decoding. So what is logical decoding? Logical decoding is the binary wall files will be converted into human understandable formats such as JSON or SQL. So when a wall is generated, a decoding plugin will read the wall stream and it will convert it into logical events. And these logical events will be given to the consumers. So logical decoding enabled the human readable formats such as JSON or SQL, and it also synced the real-time data. So this logical encoding enabled CDC and data integration. And through the CDC, we were able to connect with non-Postgres systems, or we were able to give the data to non-Postgres systems such as Kafka, Elasticsearch, and Redshift. Okay, how this CDC works? When a transaction happens through the decoding plugin, say wall to JSON, or you can, another example of decoding plugin is PG output. It will read the binary logs and it will convert them into JSON format. And this is being streamed to any non-Postgres system such as Kafka or Elasticsearch or even data lakes. And yeah, that's it. So after this, the major change came into action, which is a logical replication. So the big change happened in version 10, where the pub sub model came into existence. So far, we were able to replicate the entire database cluster. Now, from this version 10 onwards, through the PubSub model, we were able to replicate only selected tables. And this was given to the standby server. So, in addition to this selective tables being replicated, we also had the cross-version replication. That is, your pub can be of a particular version and your sub can be of a different version. And still we were able to stream the data. So this is an example of cross-version migration. Consider your pub is of version 12 and your sub is of version 17. And I have created a publication for all my tables. So initially the data, all the data from the publisher, but before that we are supposed to create the schemas in the subscriber. So create the schema and then you can start your data flow. So when the data flows completely and the lag becomes 0, after that automatically the application will point to the new version. So the upgrade of the application is complete with seconds of downtime. So this was a major breakpoint in the Postgres history. So what were the further enhancements in replication? So in Postgres version 15, we had the granularity and filtering option. That is, till now, we just evolved from whole database cluster being replicated. Then we went for table level replication. Now came row level replication and column level filtering. So in a particular table called customers, I have a column called region. I want only the regions which matches with the output Europe to get replicated or streamed to my standby. Yes, I can do it through by mentioning a where condition along with my publication. And consider I have 4 columns: ID, name, email, password. My password is very confidential. I don't want that to get streamed. I want only these 3 fields to be streamed. Yes, I can do it through column filtering. I can just mention the column names that I want to get streamed when I create the publication. So through a where condition, row level filtering is being done, and through by specifying the columns needed, column filtering is being done. And in Postgres version 16, parallel apply workers came into existence. So this enhanced your performance and the replication lag also decreased. Though we had multiple core systems, the replication was done through only a single thread. So now I want my replication to be done through parallel threads. Yes, I can do it from version 16 onwards. When I create the subscription, I have to include the variable call or the parameter called streaming is equal to parallel. In addition, in my configuration, I have to define my max parallel apply worker per subscription value. So this value will be tuned according to the resource, that is your CPU core and your network traffic. So according to that, you can tune the value. If I mention it as four parallel transactions will be handled at a time. So my streaming of data will happen quickly and my replication lag will decrease. So in Postgres version 7, the failover control came into existence where the slot persistence was done. So it is like when I have my node A failed, I say a node A and node B is there, and I have my node A failed, and my node A connects with the subscriber node C, and my node B is my standby. So when the node A fails and the node B gets elected as the new primary, the replication slot between node A and node C will be lost. So because of this, you will have data loss and you have to resync everything. So that kind of problem was eradicated from version 17 onwards. And the hybrid architecture also was hybrid high availability architecture was also enhanced in the version 17. And it supported both logical and physical streaming. So this is an example for Postgres version 17 failover control. Consider I have 3 nodes, node A, node B, node C. Node A is your primary, node B is a standby, node C is a subscriber. So the parameter which I have to tune, you have various other parameters also to be set. I'm just highlighting the important ones here. So in my node B, you can see I have to enable my sync replication slot on and my hot standby feedback on. So this will enable the shadowing of my replication slot of node A. And also it will prevent the vacuum conflicts. And in my subscriber, I have to enable the parameter called failover is equal to true. So it will resume from the crash immediately. Okay, so the breakthrough of this architecture is that node B shadows the node A's logical replication slots, ensuring no data loss is done. Yes. So why the failover parameter matters? So when we tune these failover parameters, the node B will maintain a shadow slot and it will track the wall streams, and node B will become the primary, knowing that the node C is its subscriber, and the data will be automatically resumed from the crash point. So there will be no data loss. Okay, let's get into the frequently asked questions. Can I use physical and logical replication at the same time in Postgres? Yes, we can use physical and logical replication at the same time. So when you use physical, it will give you high availability of the nodes, whereas when you use logical replication, you can go for granular data sharing. The next question is, why does logical replication not replicate the schema by default in Postgres? So the logical replication will support cross versions. Okay, so when cross version is being supported, your table structure might differ. So in that case, you need to create the schema manually. So the logical replication is designed for flexibility across versions and different table structures. Next question is, why do we use logical replication for upgrades instead of PG upgrade in Postgres? Yes, when you use PG upgrade, it will take some hours of downtime. Okay, you need to restart and all those things are there. But when you use logical replication, with zero downtime, you will be able to upgrade the version of your applications. So we have come to the conclusion. So from a very complex trigger-based system, our replication in Postgres has been evolved to a simple system. So we use the physical replication to protect our infrastructure, whereas we use the logical to empower the data. Thank you.
So before we close, a quick summary. In today's session, our speaker covered how Postgres replication started and the role of wallet replication, physical and logical replication, and how replication has evolved over time. So thank you once again, Anuja, for sharing your knowledge. And thank you to everyone who joined us today and actively participated. We will be sharing the recording and presentation slides with your registered email ID in the upcoming week. And please follow Mydbops on social media for upcoming webinars and database-focused sessions. And if you want to discuss your database challenges, you can reach out to us through the Mydbops website or on LinkedIn or by email at info@mydbops.com. Have a great weekend. I hope to see you in the next webinar. Thanks, everyone. We are closing the session now.